Thanks, Emmett. I'll be talking about our project to calibrate and validate OpenSees models for reinforced concrete walls. And this is a list of the project goals. So we're using a large experimental data set. We're calibrating, validating, and quantifying the uncertainty of OpenSees models for simulating the response of planar and non-planar reinforced concrete walls, exhibiting flexure-controlled response.
I already asked my question. What's up?
Ryan has some good questions.
Okay,
Sure.
Are we okay?
Yeah, please go ahead, Laura. Sorry, there was an open mic somewhere.
No worries. So we're looking at walls that are subjected to constant axial and cyclic lateral loading. And we're using existing published and, as possible, unpublished data, starting first with the published data set by Alex Shagay, who's at University of Auckland. It was developed in collaboration with University of Washington. And I think there's probably also, I should say that includes about 142 flexure-controlled walls tested between 1960 and 2019. And there's probably also an opportunity to use data from Abdullah and Wallace from UCLA. We're looking at using quote unquote state-of-the-art tools, Jupyter notebooks, Dakota for calibration and uncertainty quantification directly via the Jupyter notebook, but also via the NERI SimCenter QuoFem application and design safe computing resources. And the reason that we're using design safe computing resources is that we're looking at using layered shell elements with 2D concrete constitutive models by Liu et al. In 2015, and then possibly also moving on to solid elements. And so these models become pretty computationally intensive. I'd note that our project started the first of the year. And so to date, we've created the Jupyter notebooks to evaluate the OpenSees layered shell model by a comparison of simulated measure response for a limited data set. And we're working on the next steps to extend the model to include multiple failure mechanisms. Right now, we have pretty limited simulation of failure just because we're just starting. That simulation of loss of lateral strength is a big part of this project. And we're moving on to doing the model calibration via Dakota and extending our data set from right now. I think I'm going to show you 6 walls, so extending our data set from 6 walls. This is showing you some of the walls that we started looking at. These are planar walls subjected to axial load and then cyclic lateral load in the laboratory. Pretty uniform vertical and horizontal reinforcement, and then more heavily reinforced boundary elements. And we're using data from 2 test programs, Thompson and Wallace and Dossier et al. It's just an overview of the data. I guess I would note that the walls have height over length ratios that are 2 to 3. So these are slender walls. They have pretty standard material properties, longitudinal reinforcement ratio on average that are 0.5 to 1%. In the boundary element, they're 2 to 3%. And the horizontal reinforcement ratios are right around the ACI code minimum. On the right is showing you the boundary elements. None of these are actually compliant with special boundary element detailing per ACI. Most of them are too lightly reinforced for that. There's actually one that's unconfined. The NBE are boundary elements that don't comply with any of the ACI code requirements. The OBE is compliant with an ordinary boundary element, and then unconfined is, as you see, unconfined. If you look at this, there's a column that's showing P over AG F prime C. So the axial load ratios range from 6 to 13%, which is pretty standard for laboratory testing and considered reasonable for walls in a building structure, maybe a little high for a wall that was in a bridge structure. Shear demands are really low. They show a little bit of hardening if you're looking at MB over NN from 3% to 16%. And the ultimate drift capacity is like 1.5 or even 1 to 2.25. So these are not well designed walls. And I guess I'd note that in some cases, the low strain capacity for the longitudinal reinforcement is why some of the drift capacities are relatively low. And those are drifts at loss of lateral load carrying capacity. So moving on to the modeling, this is showing a simplified view of what our layered shell element looks like. So you've got the wall that is discretized into a whole bunch of square elements fixed at the base. So we're not modeling any of the bar slip out of the foundation at this point via modeling the foundation. Lateral load applied at the top under displacement control and constant axial load. Each of those little squares is this layered shell element where there's a cover concrete layer, a layer of horizontal steel, and then a layer of confined concrete in the boundary element, or just a layer of unconfined concrete if it's in the interior. And then on top of that, we're explicitly modeling the vertical steel using steel truss elements. Perhaps of note, I would also add that that means that the mesh is set up to match the location of the vertical reinforcing steel. A little bit more detail. These are 4-node multi-layer shell elements. You can have almost, I think, up to 10 layers in your shell element. We're not using that many. The concrete layers are a plain stress concrete constitutive model developed by Liu et al. 2015. It's a fixed crack model with a user-defined shear retention on the crack surface. So as soon as the concrete is loaded up to the tensile capacity, it cracks. That establishes the orientation of the crack. At that point, you have deterioration of tensile response on the crack surface and a limited amount of shear retention parallel to that crack surface. There are unconfined and confined concrete layers. The confined concrete layers, you define the strength and the compressive stress strain response using a confined concrete model like Mander et al. As I said, the horizontal reinforcement is smeared. So you have a layer of smeared reinforcement in each of these shell elements that represents the horizontal reinforcement. And that's created using ND material plate rebar, again, developed by Liu et al. And you can put whatever unidirectional, or I'm sorry, 1D steel material model you want on top of that. Right now, we're just using steel O2, but I obviously need to talk to Sashi and improve, maybe not for the horizontal, but improve for the vertical, what the steel material model is. The vertical reinforcing steel is a truss element, and as I said, we're using steel O2, but there are opportunities for improvement. This just shows you what those material models look like. I'm sure you've seen them many, many, many times, so I will not go into it. Concrete on the left, reinforcing steel on the right, and just noting that what you're seeing on the left is the behavior of that concrete parallel or perpendicular to the crack surface. The Jupyter notebooks. Right now, the Jupyter notebooks import experimental data from a database, which is just a flat Excel file. It creates the OpenSees tickle files to define the model, run the analyses, identify data recorders, and store data in a file structure. We then have other notebooks that visualize load displacement data and visualize stress and damage field data. The developing the notebook to visualize the stress and the damage field data took a while because that doesn't really exist. And it's something that you absolutely have to do when you're looking at these continuum models. So this required importing data from the model building notebook to identify the mesh, then importing the stress results for each Gauss point, mapping the stress data onto the mesh, and then creating an MP4 file. These show some of our basic load displacement histories. The orange is experiment, the blue is the simulation. As I noted before, we haven't even touched the onset of damage at this point, but so that's why you're seeing all of our blue lines heading out into infinity. We've done a lot of work previously with OpenSees modeling of damage and onset of lateral loss, lateral strength loss. So I'm not really worried about doing that. This was just really to start to, as I said, we started in January. So this is, look, our load displacement comparing simulated and measured response. We've got a ways to go on the dossier, which are the top and the bottom left. Not doing too bad on the Thompson and Wallace tests though. But again, we'll be pulling in Dakota to calibrate some of the model parameters to get better fit. This is showing the Jupyter notebook that allows us to choose, and you can barely see at the top, but you can choose from one of 9 different, or 3 of 9 different fields and plot them. I'll move on to the next one. We can talk about it. So here are some movies for RW1 and RW2 walls tested by Thompson and Wallace. They're playing, and I think will continue to play. On the left, you're seeing minimum principal stress, and that's a really good measure for showing when concrete is going to crush. So as it goes into the red, it's carrying a very low or very large compressive demand. And then as it goes to the blue, it's carrying a very small, in fact, 0. So it's going to crack, right? So it's going to carry very little minimum principal stress. And then on the right is a damage parameter. And that damage parameter goes from 0 when the concrete is uncracked up to 1 when it is fully cracked and not transferring any tension. So maybe we run RW2 again, and you can watch as it goes. You can see there the compression is building. If you're looking at the plot on the left, and then deteriorates as the concrete hits its peak compressive strength and comes back down. You can see swatches, or on the right where you see the damage, you see that the blue is this maximum damage. And so there's perhaps cracking all the way across the bottom of the wall. Let's see if I can get it to go again. Oh, we'll go back. Actually, these are the similar. So these are the dossier walls. And so if I set those running and we look at the damage on the top left, you can see that the first set of cracks just formed under loading to the right, and now cracks are forming due to loading to the left. You can see that there's some diagonal cracks that are associated with some of the change in the orientation of the stress field due to shear. In fact, if you look on the plot on the left, you can also see a swath of higher compression demand that's kind of at an angle, and that would be associated with the shear. And I'll just kind of show you all of these different movies. These movies are absolutely essential when you are working with continuum modeling, because you don't really have any other way of really understanding what's happening in the model. And so it was necessary to build out this tool for looking at these kind of data. One thing that these data are showing, at least in terms of the damage parameter, is that we're getting cracking at the top of the wall, and we hadn't bothered in our initial analyses to put in an elastic region at the top of the model where the wall is being loaded. But these data are suggesting that obviously we need to do that, because the cracking, like if you look at the bottom left, there's a big blue blob, and that cracking is just associated with the way that the load is being applied. But using these, and then, as I said, we've also got movies for normal stress and strain, shear stress and strain, maximum principal strain. You can get an understanding of where the damage is occurring, what the model's doing. As you start looking at stresses, is it reaching what you expect in terms of tension or compression? So just a tool primarily for evaluating whether or not the model is doing what we expect it to do. Even if the load displacement response looks pretty good, there could be aspects of behavior that just aren't what you expect or want, for that matter. I believe I will get another slide. There we go. As I said, the project was funded starting in January of this year. So in progress, we're extending the models to include multiple failure mechanisms, a simple steel buckling model as an example. We're extending our data set to go from 6 to many more walls, and we'll probably go through and sort of group those walls so that we're looking at different groups, maybe really low shear, moderate shear, things like that. And we're going to separate our data. So we've got some data that we're using for calibration, and then other data that we can come back and use for validation. Linking with Dakota to calibrate some of the model parameters, concrete crushing energy, concrete crack shear retention, steel buckling model, and then do some uncertainty quantification. Eventually move on to non-planar walls, maybe including a bond slip model to better capture initial stiffness, and also solid element modeling. And with that, I will end my presentation.
Thank you very much, Laura. Does anybody have any questions for Laura? I see. Michael, yeah, you had a question. You have a raised hand.
Yes, Laura, Professor Lowe's, thank you for the presentation. I was curious about your setup with Jupyter Notebooks and why you're writing tickle files from a Python-based tool like a Jupyter Notebook to do OpenSees. Have you made the leap to OpenSees Python yet? Or
So we thought about it and investigated it, and there were aspects of these models that it seemed it was easier to build out in Tickle than in Python. I will also add that the student that started working on this was not as experienced in Python as others might be. And so I think that might also have been easier for him. It was certainly something that we looked at. I will ask you, are all aspects of the Loo model in the Python version of OpenSees?
I believe so. I guess maybe we could follow up later on what particular aspects, but pretty much everything is there. So, but if there was something in particular, yeah, we can follow up.
Yeah,
thank you.
It seemed like it was the easiest path forward. We did investigate, but I'm certainly open to the idea of
and short term it probably was, but I think long term you're probably better off to do it all in Python, but that's just my opinion. Right. Yeah.
I will not take exception to that.
Okay. Thank you.
Thank you, Boris. You have a question?
Short question. So actually, now that you mentioned, so this is modeled by Tsinghua Lu, right? Group from Tsinghua, the shell model, 3D shell model.
I'm sorry, I can't quite hear you. I'm going to increase my volume a little bit.
This model that you're using for the wall, it's the shell model from Tsinghua University, right?
Yeah.
Okay, so that model
Yeah.
in OpenSees, Professor Lu sent me that model 4 years ago. There's a bug in there, and I sent him updated model, and Frank knows about it. I'm not sure which model you're using, so you need to talk to Frank, see is that the updated model or not the updated model.
What was the bug relating to?
I forgot. It was 4 years ago. It was some wrong calculation inside. Okay. There was some mishandling of some stresses and whatnot. So.
Okay, I will check with Frank on that. We haven't seen behavior that seems outrageous or problematic. Just looking at the basic material, sort of 1D material response, and then looking at the results. But I will definitely check with Frank on that. Thanks.
Okay.
I could help you out too, Laura, if Frank doesn't come through. But yeah.
All right. Are there any more questions for Laura? You're looking at the chat and the Q&A. I don't see any more. So maybe if there's no more questions for now, we'll thank Laura for the presentation, and maybe we'll move on to the next one.